All right, welcome back, future botanist, to today's explainer. Today, we're basically acting as biological locksmiths. We are going to dive right into the exact methods we use to force seed germination by bypassing nature's toughest evolutionary defenses. We're looking at why a perfectly healthy seed sometimes just flat out refuses to grow, and the honestly extreme techniques we use to break those barriers down. So here's our game plan for the explainer. First, the germination equation. Second, categorizing the 4 dormancy locks. Then we'll hit treatments 1, 2, and 3, which are scarification, stratification, and chemical stimulants. And lastly, we'll wrap up with reviving aged seeds.
Starting off with section 1, the germination equation.
You know, germination isn't just tossing some water on a seed and crossing your fingers. It's a highly complex physiological process. For a seed to actually transition from a dormant embryo to a thriving seedling, 3 main factors have to line up. The embryo must be viable, the environment needs to be favorable, and, this is key, any internal conditions preventing growth absolutely have to be eliminated. And remember, there's a strict biological order to this. The radicle, which gives rise to the root system, always emerges first. That's followed by the plumule, which becomes the shoot system.
Moving right along to section 2, categorizing 4 dormancy locks. So what happens when nature deliberately puts a biological lock on that process? Well, even in a totally perfect environment, a dormant seed just won't sprout. For us in botany, identifying these 4 groups of dormancy is everything. Group I is external seed coat dormancy. Think of the hard physical shell of a walnut or a seed coat holding chemical inhibitors like citrus. Group 2 is the rudimentary embryo, like in palmae, where the embryo literally has to physically grow more before it can germinate. Then we have Group 3, which is endogenous or internal dormancy. This is regulated by inner tissues and is super common in conifers. And finally, Group 4. This is the ultimate defense, combined dormancy. It's a double lock seen in woody trees that requires sequential, step-by-step treatments to finally crack.
To really get this, contrast the harsh external armor of Group I seeds with the invisible, delicate barriers of Group 3. Group I is intensely physical. It acts like a bouncer, just keeping water and gases out. Group 3, on the other hand, is highly physiological. It functions much more like an internal alarm clock. This endogenous dormancy can be shallow, intermediate, or deep, and it usually requires incredibly specific temperature triggers over long stretches of time just to wake the embryo up. Grasping this difference is absolutely crucial because it tells us exactly which treatment key to pull from our toolkit.
Which brings us to section 3, treatment 1, scarification methods. When we're up against the Group I armor, we often have to resort to sheer brute force. As a botanist, your job can actually get surprisingly violent. Check out these escalating mechanical scarification steps. The whole goal is to forcefully alter that seed covering to let water in. We might start simple, just rubbing seeds on sandpaper. If it's a tougher seed, we'll cut it with a knife. Or, no joke, literally crack it open with a hammer. Now, for massive operations dealing with really stubborn leguminous seeds, we toss them into huge drums lined with sandpaper or concrete mixers filled with coarse gravel. Actually, quick pro tip on that. You have to make sure the gravel is a totally different size than the seeds, otherwise separating them later is a total nightmare.
Now, if hammers and tumblers don't do the trick, we bring out the heavy chemical artillery, acid scarification. And what's truly mind-blowing here is the sheer duration. We place dry seeds in glass or earthenware containers, never metal for obvious reasons, and douse them in concentrated sulfuric acid. For some species, a quick 10 minutes is fine. But incredibly, there are species that must soak in this intense, concentrated acid for up to 6 hours. 6 hours? Just to modify that impermeable coat before we wash them down with a ton of water.
Alternatively, we can use water to strip away inhibitors and beat seed coat dormancy, but we literally push it to the boiling point. We use scalding water, anywhere from 77 all the way up to 100 degrees Celsius. We drop the seeds in for just 1 to 2 minutes, immediately pull them off the heat, and let them soak in the gradually cooling water for 12 to 24 hours. After that, you just separate the seeds that successfully swelled up from the duds. Though I should mention, some tough seeds, like the winged bean, don't need heat at all. They just need a massive 48-hour soak in plain cold water to get going.
Okay, section 4, treatment 2, stratification, also known as moist chilling. Stepping away from the brute force of scarification, we find that Group 3 seeds, the ones with the internal clocks, require a way more delicate and patient approach.
Stratification follows a very precise timeline because we're essentially faking winter to trigger physiological changes. At 0 hours, you soak dry seeds in water for 12 to 24 hours. By day 1, you drain them and mix them into a moisture-retaining medium. Then comes the waiting game. For 1 to 4 months, you store them tightly at a crisp 2 to 7 degrees Celsius. Once that's done, you have to sow them immediately. Do not let them dry out or you'll ruin the whole process. Section 5, Treatment 3, Chemical Stimulants. So what do we do when physical attacks and fake winters still aren't enough? Well, we hack the seed's internal chemistry directly. Consider this your botanical cheat sheet. For gibberellic acid, we do a 24-hour soak at anywhere from 100 to 12,000 parts per million. For cytokinins, we do a super quick 3-minute soak in 100 ppm of benzyl adenine. Ethylene, applied as ethyl, is an amazing trick used experimentally for Virginia-type peanuts. A 0.2% potassium nitrate solution works wonders on freshly harvested Kentucky bluegrass. And thiourea, a 24-hour soak in that is perfect for those really stubborn seeds that demand darkness or high heat before they'll even think about sprouting. And finally, Section 6, Reviving Aged Seeds. Before we wrap up, there's one more barrier we need to talk about. Even if a seed isn't actually dormant by design, just getting old causes it to lose its ability to germinate because natural inhibitors slowly build up over time. But here is the really incredible part. We can literally invigorate these dying aged seeds and reverse the clock on their biological decline. Through seed invigoration, we soak older seeds in 200 ppm solutions of specific orthophosphates for 24 hours. Then we dry them back to their original moisture level, plant them, and the germination rates shoot right back up. And amazingly, for a few species like papaya and chilies, you don't even need the chemicals. A simple 24-hour soak in pure water does the exact same thing. I want to leave you with this provocative thought to conclude our explainer today. From concrete tumblers and boiling water to faking winter and hacking internal chemistry, we hold the specialized keys to bypass nature's absolute toughest armor. If we can pick the biological locks of the deepest seed dormancy and even reverse aging at a molecular level to revive dying seeds, what boundaries are genuinely left for the future of global agriculture? Keep that question rolling around in your head as you continue your botanical studies. Thanks so much for joining me today. Stay curious, and I'll catch you in the next one.